Okay, good morning, Professor David J. De Los Reyes. Okay, it's October 27, 2023. The time is 4:21 a.m. Okay, my topic for decision will be what's my topic? AC machines. Okay, this will now be lesson number 48. We are still on transformers. And this is one of the most interesting topic on transformers, that is the SCAT or the TT connection, double T. Okay, let's proceed. The subject matter for this morning will be a very important one. The title will be AC machines, and this is now lesson number 48. Okay, we are running smooth, right? And the title of the subject matter for this morning will be example problem of SCAT or TT transformer, meaning the connection is the configuration letter T or SCAT. Okay, I will try to give you an example problem so we could visualize how we compute current considering the connection to be SCAT or TT transformer. Okay, a SCAT transformer is a three-phase on the primary and two-phase on the secondary. This is three-phase. If we try to measure the voltage across line number 1 and line number 2, it should be 13,200 volts. And if we try to measure between line 1 and line number 3, it will still be 13,200 volts, line 1 and line 3. And if we try to measure the voltage between line 2 and line 3, okay, the third combination, it will still be 13,200 volts. So on the primary side, the connection is actually three-phase, balance. Okay, so if these three voltages here are actually equal, it's three-phase and it's balanced. So actually, we could inject a voltage coming from the transmission line. Okay, we got line 1, line 2, and line 3, balanced three-phase. Okay, we could connect a balance voltages coming from the transmission line to the primary lines of the SCAT or DT transformer. Okay, 13,200, this is 13,200. This is 86.6% tapping, this is 50%, and this is 50%. Okay. We could prove that this is actually three-phase. Because if we try to take 86.6% of 13,200, it will be 11,431. Okay, the voltage across this. And the voltage across this winding here, they are actually 90 degrees out of phase. So this is a vertical thing. And if this is 50% tapping, 50% of 13,200 will be 6,600. Okay, so if we try to measure the voltage across this, it should be the voltage across the 86.6% tapping plus 50%, okay, on the main transformer tapping, 50%, meaning 50% of the line to line. So that's 6,600. 86.6% is 11,431. And if we try to take the vector sum of this, we will add it vectorially, and they should be equal to 13,200 volts. Okay? So meaning to say, between line number 1 and line number 2, this is 86.6%, this is 50%, the vectorial sum will be 13,200 volts. Like what I said a while ago, line number 1 and line number 2, 13,200 volts. And again, line number 1 and line number 3, 86.6% again, plus 50%, it will still be 13,200 volts. Right? And for line number 2 and number 3, This is 50%, 50%, 50% of 13,200, 50% of 13,200. The vectorial sum is still 13,200. So this is three-phase on the primary side. Okay, we'll continue the problem. I just, what you call this, explain the concept and why the primary is considered to be a balanced three-phase. Okay, so actually we could inject three line voltages here, which is balanced, right? 13,200, 13,200, and this 13,200. For a SCAT, this should be the tapping 86.6%, and this is 50%, and this is 50%. Okay, let's try to continue. Okay, I will try to erase this one so it looks good. This is just an illustration how I prove that the primary of the SCAT is actually three-phase. Okay, a SCAT transformer is three-phase on the primary, three-phase, like what I explained, and two-phase on the secondary. On the secondary side, to obtain a two-phase, this is single phase, this single phase. The end of the 86.6% tapping, we will not connect it at the median. We'll just bring it out as it is. So one end of the 86.6% is this one, the other end is this one, and this is where the load is connected. And this is to be considered a single phase. Right? And for the secondary side of the main transformer, because this is the primary side, the secondary side, okay, one end is connected to the load, and the other end, okay, is again connected to the load, and this is to be considered single phase. So a single phase plus single phase is two phase, right? So this point here is not connected to this, okay? Okay, it's not connected because like what I said, on the main transformer there are 6 terminals. So actually, whatever connection we will be doing over there, we could do it. If we would like to be a three-phase on the secondary side, we could do it. We just change the connection. But the connection on the secondary side for a two-phase will be this. Okay? Okay, I will try to continue. Three-phase on the primary, two-phase on the secondary, and the voltage is 13,200 volts. 13,200, 13,200, 13,200, okay? The secondary loads there are loads on the secondary. For the main transformer, the loads is 800 kilowatts, power factor is 1, and the voltage is 110 volts. Where is the main transformer? The main transformer is with the 50% tapping. This is the primary side, this is the secondary side. So on the secondary side, okay, we bring out two lines of the main transformer, and that's where we connect the single phase load. The total load is 800 kilowatts, power factor is 1, and this is 110 volts. This power factor, meaning it's a pure lighting load. Okay. For the teaser transformer, the total true power connected is 500 kilowatts, power factor is 1, and the voltage is 110 volts. Where is the teaser? Teaser is the transformer with the 86.6% tapping, the primary side, secondary side. So on the secondary side of the teaser transformer, there is a single phase load, in which the total value is 500 kilowatts, power factor is equal to 1, and the voltage is 110 volts. Okay, so this should be the proper connection for a three-phase to two-phase four-wire. Meaning four-wire, and on the secondary. 1, 2, 3, 4. 4 wires. Right? On the primary side, it's balanced three-phase. Line 1, line 2 is 13,200. Line 2, line 3 is 13,200. And line 1 and line 3 is still 13,200. But there should be an 86.6% tapping here, and this is 50%, and this is 50%. That's like a SCAT transformer is actually a special case of a transformer. It was designed for us to, what they call this, for it to function as a conversion from 3-phase to 3-phase, or 3-phase to 2-phase, or 2-phase to 3-phase. But for this given problem, it is from 3-phase to 2-phase. The problem is just asking, determine the current through the 3-phase lines. The problem is just asking, with these given loads on the secondary, okay, what will be the current IP1, current passing through line number 1, and what will be current passing to line number 2, designated by IP2, and what will be the current passing through line number 3, and it is designated as I sub P sub 3, okay, meaning primary current due to coming from line number 3. Okay? So we will concentrate our solution on, or our computation on the primary side. Okay? Consider the teaser winding. Where's the teaser winding? Teaser winding is this one, the one with the tapping of 86.6%. If we try to compute for the voltage across this, okay, it's not from line 1 to line 2, it's only from this 86.6% up to here. If we try to compute for the voltage across this, because this is the only one, this is the part of the winding that carries the 500 kilowatts. So if we try to compute for the current carried by this one, we must have to determine the voltage across this. And it's an easy one. It will just be simply 0.866 times 13,200. The line to line is 13,200, but at the 86.6% tapping, the voltage should only be 0.866 times 13,200. So it will just be simply 431 volts. Meaning to say, the voltage necessary, okay, to carry this 500 kilowatts is 11,431 volts. Right? Okay, I will try to bring out the so-called derivation and how to compute for the current. kVA of the primary in any transformer should be equal to the kVA of the secondary. Whatever the kVA in the primary should be equal to the kVA in the secondary. Apparent power in the primary equal to the apparent power in the secondary. Let's try to define what is power factor. It's the same from AC circuit. Power factor is kilowatt over kVA. Power factor is true power over apparent power. True power is in kilowatts. Apparent power is in kVA. That will be equation number 1. Okay. We'll try to bring out the formula and how to compute for kVA. We'll remove first the K. What is volt ampere? The product of voltage and current, right? The volt ampere is actually the product of voltage times current. So this is now with the subscript P1, this is with the subscript P1, meaning we are referring to primary side number 1. For it to become a kVA, we will divide this by 1000, so this will now be a kVA. Right? Therefore, the equivalent of kVA instead of voltage and current, okay, it should be the product of voltage and current on the primary side, all over 1000, we call this equation number 2. Okay, going back to equation number 1, power factor now, I will now put the subscript 1. It refers to the primary side considering the teaser transformer. This should be the total load on the teaser. Whatever load on the secondary, it will still be the load on the primary, okay? So this should be kilowatt number 1 with the subscript 1 already. Okay, and we will replace kVA by this equation number 2 here. Okay, BP1 IP1 over 1000. Or if we try to simplify this one, power factor with the subscript 1, meaning it's the power factor of the teaser transformer and the primary, should be equal to kilowatt number 1. Okay, we change the operation from division to multiplication, so it will be kilowatt 1 over 1 times, this will go up, with the reciprocal of this will be 1000 over the product of BP IP. And if we try to compute for IP1, okay, IP1 now will be kilowatt number 1 times 1000 is this. all over BP1, we take this power factor underneath because we are computing for IP1 all over power factor number 1. So this is actually a general equation on how to compute for the current for a teaser transformer considering the primary side. Right? What is the load of the secondary teaser? It's 500 kilowatts, so this should be 500 kilowatts. Right? This 1000 is just a, what you call this, conversion factor. And the voltage that carries this 500 kilowatts is actually, it's only this voltage here. It's the voltage that comprises the 86.6% winding. So if we try to compute for BP1 is actually 0.866 times 13,200, and that is actually 11,431. So what goes under BP1 will be 11,431. It is not the 13,200 because the tapping on the teaser is only up to 86.6%. So this is 11,431 come from this, multiplied by 1, the power factor is 1, and what will come out for the primary current is 43.7 amperes. It's a small current. Why it is small? Because the voltage across this is big, right? Big voltage, small current. So if we try to compute for the current on the secondary, there's a problem. Why? The voltage is very low. It's 110, right? It's 110. Okay? So for this 500 kilowatts to be equal to the 500 kilowatts on the primary, the current should be very big. And if we try to compute for the current here, it's actually 45 amperes, 4,545 amperes. Okay? Big current, small voltage, big voltage, small current. Okay? So this is the current that passes through the line number 1. For the main transformer is actually the part of the transformer that has a 50% tapping. Okay? This is the primary side. This is the secondary side. And the problem is asking what will be this current here and this current. This current here and this current are actually equal. So to compute for their values, we'll just need to compute for the value of one value. Then we equate it because they are equal, right? So consider the main transformer. Okay, again, using this formula. Okay, the right formula. But we will now try to change the subscript. We are now, what do you call this, IP2. It will now be IP2, right? IP2 now will be kilowatt number 2 times 1000 over BP2 times power factor number 2. Okay, if you try to notice it, the tapping on the main transformer is actually 50%. Okay, so the current that will pass here will just carry the total load is 400 kilowatts, right? But this is 50% and 50%. Okay, so the current on this line here should be equal to this, so they will subdivide the load. So the total kilowatts now will be the total load on the secondary. Okay, this is over 2. To compute for the current passing here, we'll just need the total kilowatt, okay, carried by 8. And it should be 1/2 or 50% of 800 kilowatts. So this is actually 800 over 2 times 1000 conversion factor. Okay. And the voltage across this, if this is 13,200, this should be 6,600. This is 6,600. They are in phase, right? So 6,600 is actually 13,200. So the voltage across this should be 13,200 over 2 times the power factor 1. And the value of IP2 will be 60.6 amperes. And again, if we try to compute for the current passing here, it will be the load carried by this one. Okay, then we use the voltage across it also, but they are equal. So IP3 will still be equal to 60.6 amperes. Right? Because if we try to use this formula, the load carried by this winding here will be 50% of 800 kilowatts. It will still be 800 over 2. And the voltage across this will still be 1/2 of 13,200. They are in phase. Okay? 13,200 divided by 2, that will be 6,600. So this will still be 6,600 times 1. So obviously, IP2 is equal to IP3. And their magnitude is actually 60.6 amperes. And again, if we try to compute for the current in here, okay, this is 800 kilowatts, okay, this is only 60.6, but if we try to compute for the current on the secondary, since the voltage on the secondaries are only 110 volts, okay, supposed to be, if we try to compute for the current, we'll use the pole 800 kilowatts divided by 110 here. What will come out will be 7,273 amperes. Right? It's a very big current. Okay? Okay? Very big current. 110 volts, 72, 73. And this is 60.6, but this is 13,200. Right? Big voltage, small current. Big current, small voltage. Okay, that's it, guys. That's how we compute currents for SCAT or TT transformer. For the meantime, the given example is a conversion from 3-phase to 2-phase. Okay, 13,200, 13,200, 13,200. And the proof of this is that this one here is, how much is this one? 11,431. This one is 6,600. If we try to take the vector sum, this should be 13,200. Okay? The voltage across this 86.6% winding plus 50% is 13,200 volt. And again, if we try to compute for the voltage across this 86.6 and 50%, it will still be 13,200 volts. And if we try to compute for the voltage across line number 2 and number 3, okay, it's 13,200. This is 6,600, 6,600. This is 13,200. Okay, so it's a balanced 3-phase. Okay, that's it, guys. This is Professor David J. De Los Reyes. Good morning from Los Angeles.